Okay, so good afternoon, all of you. I am Simran. Today we are going to discuss for the week 3 lecture of the topic Introductory Organic Chemistry Second, which is running on the NEPTEL platform. And the course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre. So I am your PMRF teaching assistant, and today we are going to discuss about the carboxylic acid and its derivative, which is the week 3 course. So I hope you guys have gone through my previous videos. And if you have any doubt regarding that tutorials, then please let me know so that we can take up your questions. So you guys have any doubt?
No, ma'am.
Okay. So shall I proceed with week 3?
Yeah, ma'am. Sure.
Okay, thank you. Okay, so the content is carboxylic acid and its derivative. So here is the first problem. So the first problem is benzoic acid reacts with phosphorus pentoxide in the presence of heat to give what? Option A, B, C, and D. We have to figure out what is the carboxylic acid and how it is going to react with phosphorus pentoxide. So this is the primary structure for the benzoic acid, and phosphorus pentoxide is a dehydrating agent here. So, dehydrating agent is which abstracts water molecule from a particular compound. So here the benzoic acid is this. So phosphorus pentoxide is acting as a dehydrating agent in the presence of heat. So we have to follow that what is the major compound which is getting formed out of these four. Okay. So the reaction of phosphorus pentoxide with acid is going to give you an anhydride. How? See guys, here in the place of R we have the benzene group. This, right? Now in the place of R we have benzene and this is a benzoic acid. So now P2O5, which is a dehydrating agent, will lead to abstract a water molecule from your compound. So how it is going to take up the water molecule? First of all, the P2O5 can be written as this expanded form. Oxygen abstract a hydrogen, that is a proton, from the carboxylic acid and leads to formation of a carboxylate ion. This carboxylate ion then again attack on the phosphorus atom and this PO3, which is a good leaving group, leaves out. Now, this species is getting formed. Again, another molecule of carboxylic acid attacks on the carbon because we have discussed that carbonyl in the carbonyl compound, the carbon is electron deficient species and oxygen is an electron rich species. So here, oxygen attacks on the carbon of the carbonyl group, and again, this particular species knockout. That is H2PO3 is two byproducts which are getting formed here, that is PO3 and H2PO3. Now again this molecule is getting reacted on this particular carbonyl species. This kind of tetrahedral intermediate is now getting formed. So this carbocation is neutralized by the hydrogen atom, and then this anhydride formation is getting placed. So this kind of mechanism is operative when we have a carboxylic acid and a P2O5, that is a dehydrating agent. So basically the dehydration of acids will lead to generation of anhydrides in the system. So if we consider regarding to the question, if we consider this benzoic acid in the place of this particular thing, now, two molecules of benzoic acid will react together to give a anhydride. Now, here both R are benzene groups. So, what we have here is benzene, that is PH, CO, and a pH again. So, an anhydride formation is taking place. So, amongst all of these options, so according to you, which is the perfect answer? Can you tell me if you have learned the concept or gone through the mechanism?
Ma'am, option D is the correct answer.
Option D. See, we have a carboxylic acid, right? So this carboxylic part, this PH is same for all of these options, right? But what happens here is another molecule of this carboxylic acid, one of the H is getting attached from that, and another OH which is getting from another molecule of this carboxylic acid, here the water molecule is getting released. Okay, so what you have is this pH COO. Again, you have here an carbonyl group, right? And a pH. This again a benzene ring is there, right? So what you have here is a pH carbonyl group O CO and again a benzene ring. So now tell me what is the correct answer. Now C6H5 you have, right? C6H5 you have. Again you have a CO O CO and a pH. I'm writing is at pH, that also means a C6H5. So now tell me how many oxygens are there? Three oxygens, right? So which is the correct answer now? It is it D or C? It is D, right? So have you got the answer? Any confusion?
Yeah. No, ma'am.
Okay, so here phosphorus pentoxide is acting as a dehydrating agent. So when you have an acid in the system, you will end up with a anhydride. Okay, so now I'm going to the problem 2. So it is a very nice question. If you gone through the particular system of acidity, which we have talked earlier also about the carbonyl groups, so you can simply answer this if you got the mechanism right now. So they are asking in the compound given below, that is this, the correct order of the acidity. So they are asking the correct order of acidity of the position X, Y, and Z. So they are asking which is more acidic. So acidic, we have talked about that the acidic hydrogen is which, that is very electron deficient. So the carbon here is very electron deficient, and then it makes the hydrogen more electron deficient. So we are saying that it is an acidic proton, right? So now we have to figure it out that which is the most acidic hydrogen, and we have to arrange it in a order, particular order. So here we have three kind of hydrogens, right? One of this COOH and two of this amines hydrogens. So we have to figure it out that which is more acidic. So as we know, this is an acid group, this is an amine group, both. So according to you, which is more acidic, an amine hydrogen or a acid proton? Which is more hydrogen? Oh, sorry, which is more acidic? Any guesses? See, more acidic means that after removal of this hydrogen, the negative charge which is getting created is stabilized more, right? So, in the case of acid, when you leave this hydrogen as such, and negative charge is created on this oxygen, like this. We have this in the system, right? This O and this OH. So, after removal of this hydrogen, this carboxylate group is getting formed, right? So this negative charge is now stabilized by the conjugation. But in the case of amine, if we look at this NH, and if I remove a proton from here, then it will be end up with an amide, NH minus, right? So is there any stabilization in this case? By conjugation, I'm saying. This negative charge is stabilized by this electronegative nitrogen. Okay, but is it the carboxylate in which the negative charge is more stabilized, or it is the NH amide group in which the negative charge is more stabilized? What do you think? Any guesses?
Ma'am, I think option A is the right answer.
Option A. See, don't go to the options, right? What I am asking here is the carboxylate ion proton is more acidic, or this amide proton is more acidic? See, How we are going to check it?
Carboxylic is more acidic, ma'am.
Yeah, carboxylic is more acidic. How? Now we have to just simplify that how it is more acidic. So see, when you remove a proton from here, this carboxylate group, and carboxylate ion is getting generated, right? This minus charge is getting generated on this oxygen, which is in conjugation with this carbonyl group. So by the plus R effect, it is actually stabilizing this negative charge. But here, in the case of amine, if you abstract a proton, then an amide is getting formed. Now here N contains a minus charge, which is although stabilized but not at much extent as in the case of carboxylate, because here minus I effect of this N nitrogen, that is the electronegativity of this nitrogen, is playing role for stabilizing this anion. But here, in the case of carboxylate, there is a resonance stabilization, which is more prior than in the case of amide. So here, it is more acidic than the amine. So first option, that is like this X, is very acidic than both of this amine. Have you got the answer? Because in the case of amine, if you abstract a proton, then you will end up with an amide group, that is NH minus. Now this negative charge is stabilized by nitrogen due to the electronegativity. Okay, but now uh, is there any conjugation through which it is stabilized? No. In the case of carboxylate, although there is a conjugation as well as the minus I effect, so both things are there in the case of carboxylate. So this carboxylate proton is much more acidic than the amines. Okay, so both of these amines having lower acidic protons than the carboxylates. So first of all, we get to know that this X, that is this proton, is very acidic than Y and Z. Okay, now we have to look into it that which of Y or Z, which of these both have more acidic proton, right? Which of these do have more acidic proton? Now, is this Y or Z? We have to figure it out. Now, in the case of this Y, you will have an NH minus, that is minus on this particular nitrogen, and in the case of Z you will have a minus on this particular nitrogen after the removal of proton. I'm saying, okay. So here this negative charge is now stabilized by this nitrogen electronegativity, as well as there is an electron withdrawing group which is present at the adjacent position of this amide, that is the carboxylate group. As we know that this carboxylate group is an electron withdrawing group, right? It is the electron withdrawing group. So now this negative charge is stabilized both by the electronegativity of the nitrogen as well as the electronegative electron withdrawing nature of this carboxylic acid, which is present at the adjacent position of this group. Okay. So this carbon have both amide group and the carboxylic acid group. So this negative charge is stabilized by nitrogen as well as the electron withdrawing effect of this carboxylic acid group. Okay, but in the case of this Z proton, when we abstract a proton from the Z species, this negative charge is stabilized by this nitrogen only. There is no electron withdrawing group which is present adjacent to this particular Z species. This carboxylic acid group is very far away from this Z to stabilize this negative charge. Okay, so here now the question arises, is the Y is more stabilized or the Z is more stabilized? So what do you think?
Y is more stabilized,
Yeah,
ma'am.
so Y is more stabilized. Okay, so if you, so the abstraction of proton from Y species is very facile than Z species. Okay, so what we can write here, which is more acidic, Y or Z?
Y is more acidic, ma'am.
Very good. So here Y is more acidic. Got the point? So Y is more acidic than Z. So this will be the correct order. So which matches from the following? B is the correct option. Okay. I hope this question is clear to all of you. If you have any doubt, please ask me.
No, ma'am.
Okay. So I am proceeding to problem 3. So here in the problem 3, which of the following order of relative strength of acid is correct? So we have to justify that which is the correct order of the strength of acidity of acids. Is it A, B, C, or D? So I am just uh, expanding these particular acidic things. So we have to justify the order of acidity of this particular acids. So order of acidity. Acidity means how how fast this acid will leave the proton. So the negative charge, again the same concept. How much this negative charge is stabilized will define the acidity of the acid carboxylic acids. So now, if you abstract a proton from A, B, and C, these kind of negative charge are created from on this oxygen. That is, a carboxylate group is getting formed, right? So now you have to figure it out which is more acidic. So now the negative charge is much more stabilized in the case of what? Which is the more acidic proton. So the acidity depends how facile or how fast the proton abstraction is into the acid. So if this acid is present in the system, how fast you can abstract a proton from this acid. So how fast it will give you the proton, it depends on the acidic strength of the acid. So strength of acid directly depends on the ease of abstraction of the proton. Okay. So after the abstraction of this hydrogen, after giving the hydrogen, a negative charge is getting created on this oxygen. That is, the carboxylate ions is getting formed. So now you have to see in which case this negative charge is stabilized more. Okay. Stabilized in all the cases, we have to know, right? So in which case the stabilization is very much. So we have to figure it out. So now here different halogens are attached to this carbon. So this adjacent carbon have different halogens which are attached. So we know that this fluorine is much more electronegative than chlorine and then bromine, right? So now the electronegativity depends on the how facile the particular element abstracts or just abstracts the electron density towards itself from the adjacent carbon, right? We have talked about the electron negativity in the previous lectures, right? So here the fluorine is much more electronegative than chlorine and bromine, so it will abstract the electron density towards itself very much. So here fluorine is taking the electron density towards itself, right? Which is very low in the case of Cl and which is again very low in the case of Br, because the electronegativity trend decreases when we are going to fluorine, chlorine and bromine. Okay. Is this thing clear?
Yes, ma'am.
Okay. So if it is clear, then you get to know that this negative charge is now stabilized more because of the electronegativity of this fluorine. Now this negative charge is in conjugation with this carbonyl, right? And due to which it is again stabilized. This is the case in all the three, that this negative charge is stabilized due to the resonance. But one of the difference here is that the adjacent carbon has another halogen, right? So which of the halogen will stabilize this negative charge will lead you to the answer. See, fluorine is stabilizing more this negative charge. How? Because of the electronegativity, it is pulling the electron density towards itself, right? So this negative charge is spreaded over this particular trend. So this is how it is stabilizing this negative charge. But in the case of chlorine, which is less electronegative, it is also stabilizing this negative charge, but it is less electronegative than fluorine. So the stabilization is less than fluorine in the case of chlorine, right? And which in turn is also be in the case of Br, it is also although less in the case of Br than the chlorine and fluorine, because Br is again less electronegative than the chlorine and fluorine. Okay. So the stabilization is there. I'm not saying that it is not stabilized. It is stabilized. But how much stabilized you have to know. So now the much more stabilized species here is the fluorine. Right, this acid which is connected to this fluorine atom is higher in stabilization. So now this negative charge is much more stabilized in the species A, then species B, and then species C. Okay. So just tell me which is more acidic, the species A, B, or C?
A species is more acidic, ma'am.
Yeah, A species is more acidic because the abstraction of hydrogen is very, very easy because the negative charge is very much stabilized because of the carbonyl group conjugation as well as the fluorine atom electronegativity. Okay. And again, now if you have to compare between the B and C, which is more stabilized?
Chlorine is more stabilized, ma'am.
Very good.
Option.
Yeah. So the trend which matches to this order is like this. It is more stabilized, which is in turn is more stabilized than bromine. Okay. So which option is correct?
Option A, ma'am.
Yeah, option A is correct. Okay. So is it clear to all of you?
Yes, ma'am.
Okay. So I'm going to problem 4. This is the explanation that due to the minus I effect of these fluorine, chlorine, and bromine, option A is correct. So now the problem 4. So guys, here the correct order of reactivity of PHMgBr with, as you know, this PHMgBr is the Grignard reagent. Have you heard about the Grignard reagent?
Yes, ma'am.
Yeah. So this is the Grignard reagent. So they are asking the correct order of reactivity of this Grignard reagent for this first, second, and third species. So here see, what happens here is in the Grignard reagent, this magnesium Br is positive, and here this is the anionic species which is present. Okay. So here pH has to react with these first, second, and third species to give you the product. Okay. So, as you know, that this carbonyl carbon is much more electron deficient than oxygen. So, this pH is going to react with this carbon only, okay, of the carbonyl group because it is electron deficient and it is electron rich in nature. So, now you have to figure it out that which is more reactive for this nucleophilic attack. So what happens? So Grignard addition to aldehyde and ketone work in a stepwise manner. Okay. So first step is the addition step. So here, this negative species, which is here, this negative species is attacking on this carbonyl carbon, and this tetrahedral kind of intermediate is getting generated. Now this tetrahedral intermediate, after the workup, take up some proton from the system, and an alcohol is getting generated. So these kind of two steps are operative in the Grignard addition. First step is the addition step and second is the protonation step. This is how it works. So now they are asking the reactivity. Although this species will interact with all of the three as we know, but now the reactivity depends on how electrophilic this center is, because what happens there is a nucleophilic attack is taking place, right? This nucleophilic attack is taking place. So this species, if the carbon is much more electrophilic in nature, this attack is much more facile. Okay. So we have to figure it out that which is the more electrophilic carbon so that the reactivity can be justified. If the carbon is very, very electrophilic in nature, then the nucleophilic attack is more facile and the reactivity of this Grignard reagent to particular compound is high. Okay. So now coming back to the question, that the first species, second and third, look all of the three species. Which carbon is much more electron deficient in nature? We have talked about in the previous lecture of the carbonyl compounds. This concept we have talked about. So according to the concept, first, second, and third, which species is having more electron deficient carbonyl carbon? According to you, any guesses? See, as we know that this carbonyl carbon is electron deficient in all of the three cases, okay? But we have to figure it out that which is the more electrophilic carbon. See, in the case of second, you have two substituent which is connected to this, a methyl and a hydrogen. This is an aldehyde, this is a ketone. So now this carbonyl carbon is electron deficient in nature, right? So this methyl have a plus I effect, as we know. So this plus I effect increases the electron density at this carbon, right? Making this electrophilic carbon less electrophilic. So, because of the presence of two methyl groups, two plus I effects are there. So, both of the methyl will induce a plus I effect and increase the electron density at this particular carbon in third species. So, the electrophilicity of this carbon is less than this second species. Why? Because here we have only one methyl, which is going to give you a electron density here, and one of the hydrogen substituent, it is not going to increase the electron density of this particular carbonyl carbon. So the electron deficiency of this second species is higher than third species, because the two substituent which is connected to to this second species is methyl and hydrogen. Here methyl is going to increase the electron density on carbon, true, but what happens here is that in the case of species 3, this 2 methyl group will again increase the electron density at the particular carbonyl carbon, and the electrophilicity of the second species is higher than third species. Okay, and in the case of first, what happens here is pH, that is the benzene ring, which is getting in the conjugation with this particular carbonyl group. So these both species are in the conjugation with this carbonyl group. So there is a particular partial double bond character which is arising between carbon and this pH carbon. So just assume this. If you have this benzene ring, okay. See, if you have this benzene ring, then you have this. Okay. So now this is the case in the species 1. Okay. Have you got that second species is more electron deficient than third species? Now we have to figure it out that first species. In the case of first species, how it is related. Okay. So now we have this kind of double bonds in the benzene ring. Okay. So they are present in the conjugation with this carbonyl group. So there is a double bond, partial double bond character which is arising between this carbon and this carbonyl carbon, right? So in both the cases, this pH is in conjugation with this carbonyl, and there is a partial double bond character which is arising between these carbon and these carbon. So this is making it less electrophilic in nature than this ketone as well. Have you got this point?
Once again repeat that, ma'am.
Sorry.
Ma'am, please once again repeat that, ma'am.
Okay, okay. See, what happens here is you have to first figure it out that all of the three which is more electrophilic carbon, because we have talked about that this carbonyl carbon is in turn electrophilic in nature, right? So now if it is electrophilic in nature, only then this Grignard reagent will going to attack on this carbon, because it is a nucleophile, right? So if you give more electrophilicity to this particular carbonyl carbon, then the attack of this nucleophile is much more facile, right? So now then only we can talk about the reactivity. So first we have to figure it out that which of the carbonyl carbon is more electron deficient in nature. Is it first, is it second, or is it third? So first of all we have to compare this aldehyde and ketone. Okay, so in the case of aldehyde, we know that two substituents are there, that methyl and hydrogen. So only one substituent have the plus I effect, right? So they are increasing the electron density from one side only to this particular carbonyl group, so making it less electrophilic because it is increasing the electron density at this particular carbon. But in the case of ketone, as we know that these both methyl groups are present, so both of them have the plus I effect, so both of them in turn increasing the electron density at the carbonyl carbon, so making this carbonyl carbon less electrophilic. So if you compare the second and third, which is more electrophilic in nature? This aldehyde species is more electrophilic in nature. Why? Because there is only one methyl which is increasing the electron density at the particular carbonyl carbon. Is it clear? This much?
Yes, ma'am.
Okay. If this much is clear, then you can easily answer that particular this aldehyde is less electron density, having the electron less electron density at this carbonyl carbon than the ketone. Now we have to figure it out that in the case of this benzophenone system, what is happening. So see, these two benzene rings are there and this carbonyl group are there. Okay, so if you assume that this carbon this pH is in conjugation with this carbonyl on both the sides, these pH rings is in conjugation with this carbonyl group. Okay, so there is a particular partial double bond character which is arising between these. How you can write it? See, the resonance structure is how we can write it. This is the resonance structure. See, okay. So I'm just missing a pH here. So just try to this kind of thing. Okay. Sorry. Hmm. Okay. So there is a partial double bond character between these two carbon, and again you have this kind of species. Okay, and there is a again a pH group which is attached. Sorry. So this is the case. Okay, so just try to think that if the conjugation is taking place from here, there is a delocalization. So there is a partial double bond character which is arising between these carbons. So this carbons is this carbon and the pH carbon. So there is a partial double bond character which is arising here. Okay, so this is making this particular carbonyl carbon less electrophilic in nature than the aldehyde or ketone, because in this case both the pH is involved in the conjugation. So both in the both side you have a conjugating structure in which there is also a double bond character which is arising from this side also. Are you getting my point now?
Yes, ma'am.
Okay. So see, so now it is although less electrophilic in nature than ketone, because here the resonance effect is coming into play. It is in the case of ketone, there is only plus I effect which is making the carbonyl carbon less electrophilic. But here in the case of benzophenone, here in the case of first species, two phenyl groups are there. So two phenyl groups are imparting the plus R effect. So this there is a partial double bond character which is arising between the carbon of the phenyl ring and the carbon of carbonyl group. Okay. Also, both on the both the sides there is a partial double bond character of which is arising there. So now these two pH will make the carbonyl carbon much electron rich than ketone. So, if we consider the electrophilicity order of this carbonyl group, so which is more electrophilic in nature? This second species is more electrophilic in nature than third species, which in turn is more electrophilic in nature than first species. Are you agree with me?
Yes, ma'am.
Okay, no doubt, right?
Yeah, ma'am.
Okay. So if you agree with me, this is the correct order of the electrophilicity. So just tell me that the correct order of reactivity will be, because see what happens here is if the electrophilicity of the carbonyl carbon is high enough, only then this nucleophile will attack on the particular carbonyl carbon and yield you the product fast. Okay, so reactivity here is in the sense that how fast it will react to give you the product. So if the electrophilicity of the carbonyl carbon is high, then the nucleophile will react with it very fast to give the product. Okay, so now just tell me that if this is the electrophilicity order, then what is the correct option of the reactivity? Means how facile this nucleophile can attack.
Option C, ma'am.
Option C. Yeah, option C will be the correct answer. How? See, there is a two factor which is coming into play here. First factor is the electrophilicity of this carbonyl group, okay, and second is the steric hindrance. We we do not just see that there is no steric hindrance. See, the nucleophile is bulky, which is phenyl group, okay. Although this option is correct, but you have to consider two concepts in mind. First is the electrophilicity, which we have talked about, and second is the steric hindrance. So here the bulky group is there as the nucleophile. So if your substituents are less hindered, then also the reactivity is very fast. So here in the case of one, two phenyl groups are there, which is very bulky. Okay. Then two methyl group, which is in turn very bulky than the one methyl and hydrogen. So the bulky order of bulkiness will also be the same. That first, second is less bulky, then third, and this first is much more bulky. So bulkiness, as it increases, it decreases the reactivity. So you have to first look into it that first order is the electrophilicity order and second is the order of bulkiness. So both are coming into play in this particular solution. So amongst this, now consider both of these things and just tell me that have you just understood what I have said till now? Have you understood all the things, the bulkiness, the electrophilicity? If anything is not clear, just ask me.
Ma'am, when the order of, bulkiness is increases, then
Yeah.
reactivity is decreases. Am I right, ma'am?
Yes, yes, you are right.
So, ma'am, I have a doubt.
Yeah, please.
In this case, a steric effect also plays a role, ma'am.
Yes, yes. In this case, is steric hindrance is playing role because see what you have here is the nucleophile, which is bulky. Okay, if you have an hydrogen instead of this phenyl ring as a nucleophile, does it matters that which of the conscious substituents which are attacking or which is present on your carbon? Does it matter? No, because now the hydrogen is very small, right? So it will adjust. It will doesn't impart that much steric hindrance to your system. But here the nucleophile is bulky, which will affect your reactivity. If the system in turn is very much bulky and now you are attacking a nucleophile which is also very bulky, so does it stabilize? No, it is not stabilized, right? So that's why in the case of bulky nucleophiles, this steric hindrance order will come into play. Otherwise you have to see the electrophilicity order of the carbonyl carbon only. Have you understood?
Yeah, ma'am.
Okay, any doubts?
No, ma'am.
Okay, there is no doubt. Then, see, the answer is the presence of bulky group around the carbonyl group creates a steric hindrance for the attack of Grignard reagent. So the correct option is C. So I hope you guys go through the particular video again, and if anything doesn't clear or if anything bothers you, just tell me. I will let you know in the next lecture. Okay. So I'm coming to the problem 5. So see, here the acid which is produced in the below sequence, you have to figure it out which is the Y which is getting formed here. So this is the sequence of reaction which you have to look into it to get the product Y. Okay. So first of all, you have this kind of system that is C2H5I. That is the ethyl iodide. Okay. So if you treat it with an alcoholic KOH, so what will it will give you? Alcoholic KOH generally abstract a gives you a beta elimination reaction. So what is beta elimination? So the carbon which is present in the beta position of the halogen carbon which is attached, it just abstract a proton from here and a HBr molecule, that is a neutral molecule, is leaving. So in the case of alcoholic KOH, what happens? You will end up with an alkene from the halogenated product, halogenated reactant. So in the case of, if we consider that we are treating it with an alcoholic KOH, alcoholic KOH will give you an elimination product. Just keep in mind that alcoholic KOH will give you an elimination product. How? It KOH, as you know, is a base, right? So it will abstract a hydrogen from this particular position, that is a beta position. This is beta and this is alpha in the in the respect of what? This halogen. Okay. So it will abstract a beta hydrogen from here because it is a base. So it is forming an carbon ion at this position. So now this carbon ion will shift here and will lead to the removal of this iodide. This iodide knockout. So an alkene species is getting formed, right? So what will you end up with? A ethylene. You will end up with a ethylene unit. This carbon, double bond, and a carbon. Okay. These are the hydrogens which are present. Fine. So this is the mechanism how it is operative. First of all, this alcoholic KOH abstracts the proton from this particular beta hydrogen. Why? Because this halogen will make this beta hydrogen more acidic because of the electronegativity effect. Okay, so it is making this beta hydrogen more acidic, and that is why this alcoholic KOH is capable of abstracting a proton from this side. And now, after abstracting a proton, a carbon ion is getting formed here, and which goes here, and then which leads to the formation of this ethylene unit and a Br knockout. So you are having from a halogenated species, you are having a alkenes, right? So elimination product is getting formed. So same in the case of this, you will end up with a ethylene. So the X unit here is ethylene. See, this X unit is ethylene. Okay. So now they have treated this ethylene unit with bromine in CCl4. So bromine in CCl4. So the reaction mechanism here is, first of all, this ethylene unit, this bromine is polarized, right? So we have this bromine like this. This is Br with and Br. We have this Br and Br unit. Br attached with again a Br. This is bromine. Here, one is positive and one is negative species because bromine species is polarized. So one Br molecule is electron deficient and one Br molecule is here is the electron rich in nature. So first of all, this ethylene, as this pi bond is electron rich, it will attack on the bromine atom, and here a bromonium ion species is getting formed. After that, another Br minus, which is knocking out here, attacks on this particular carbon, and this Br leaves out. So this 1,2 bromo product is getting formed in the system from this ethylene unit. So bromine in CCl4 will give you 1,2 bromo ethylene, sorry, 1,2 bromo ethane in the system. Okay, so from the ethylene you are ending up with the 1,2 bromo 1,2 dibromo ethane. Okay, so this Y species is what? This is the Y species here which is forming. Are you understood the thing till now?
Yes, ma'am.
Okay. If you have any doubt, just ask me, guys. Okay. So first of all, we are starting up with this ethyl iodide, and in the case of alcoholic KOH, when we are treating it with this, then alcoholic KOH will abstract a proton from this beta hydrogen because it is more acidic, and now a carbon ion is getting formed here. So now it rearranges to knock out this iodide, and a alkene is moiety is getting formed. So this is your X ethylene, and again they have subjected this ethylene in the condition of bromine CCl4. So first of all, this ethylene is electron rich in nature, and it attacks on the bromine which is electron deficient, and formation of a bromonium ion is taking place. And after that, another bromide ion which is knocking out from here attacks on this particular carbon to lead you 1,2 dibromoethane, which is Y here. And okay, and now they have treated this 1,2 dibromoethane with KCN. What will it do? KCN, as you know, it will replace both the Br with cyanide group because it's a nucleophilic substitution kind of reaction. So both of this Br, because it is a good leaving group, as you know that the bromo are the good leaving group, so Cn minus will replace these Br molecule by the electrophilic substitution reaction, nucleophilic substitution reaction, sorry. So these Br are replaced by Cn moiety. So you now have both of the Cn group in the place of Br. So you have this Cn group. So what you have is 1,2-dicyanoethane. Okay. So if you are treating this Y with KCN, then Z is the 1,2-dicyanoethane. It is occurring due to the nucleophilic substitution reaction only. Now, if you have this 1,2-dicyanoethane, okay. So here they have treated it with now they have treated it with water. In the case of H2O, what will it go? That if you have this kind of system in which we have cyanide, Cn. Now, cyanide in the case of water hydrolyzed to give you an acid. So, this is the particular mechanism how it is going to give you an acid. So, if both the cyanide will give you an acid, what happens that this carbon and this carbon, we have 2CN which is attached. Okay, right? Because we have started with ethyl iodide. Okay, so we have two systems, two carbon in the system. So this is hydrogen, 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 and this is again hydrogen. Okay. So if you have two cyano in the system, then what happens according to this mechanism? You will end up with an carboxylic acid. So both of this cyano group will convert into carboxylic acid group. So what you will end up with is this particular Cn group will convert into this carboxylic acid group by this particular mechanism. Okay, first of all, what happens here is in the cyanide species, this nitrogen is negatively charged. So this nitrogen first abstracts the proton from this hydronium ion, and after that, this water molecule will interact with this carbon because now here it is electron deficient in nature. So this positive charge on nitrogen will get neutralized, and this kind of species is getting formed. So after tautomerism, there are the tautomerism of this particular species. They are the tautomer. These both are the tautomers. Okay. So after the tautomerism, this OH2 again interact with this carbon. This water molecule and again interact with this carbon to form this di alkoxy type of thing. And after the proton transfer to this nitrogen, this elimination is taking place to give you alcohol. So just go through this mechanism very deeply. You will get to know that this particular cyanide is converting into carboxylic acid, giving you a byproduct that is ammonium ion. Okay, is it clear?
Yes, ma'am.
Just tell me if you guys have any doubt. Okay. So first of all, we have this ethyl iodide in hand, okay, and then we have treated it with this alcoholic KOH. So this alcoholic KOH will again give you an eliminated product, and now an alkene formation is taking place. That is an ethylene. Now this ethylene is subjected in the case of bromine and CCl4. Now we have seen that by this particular mechanism in the bromine and CCl4, 1,2-dibromoethane is getting formed. After when they treated with this KCN, this potassium cyanide will undergo the nucleophilic substitution reaction in which they replace the both Br group with cyanide because these Brs are good leaving group. So this cyanide is getting substituted in the place of Br. So after the hydrolysis, they will end up with this particular dicarboxylic acid group. Okay, so this is what we have to. Now coming back to the question, we have this kind of system. So now, which of the four is the correct option? So now this particular moiety is known as succinic acid. So this is the succinic acid. So the first option is correct option. That is, we end up with Y. The Y is the succinic acid. Now all of these particular reaction will yield you a succinic acid. Okay. So why is the succinic acid? Is it fine or I have to repeat something?
No, ma'am. Clear, ma'am.
Okay, okay. Now we are going to problem 6. We are lack of time actually. So here in the problem 6 they are asking again the same set of question that the reaction in a set of reaction acetic acid yields a product D. This acetic acid, they are starting with the acetic acid and now they are ending up with the product D. So then we have to justify the structure of the product D. So we have in hand acetic acid. So see, acetic acid they have treated in the in the presence of SOCl2. So what happens here is, in the case of acetic acid or in the case of acid, when we treat it with the SOCl2, what happens? This oxygen, which is electron rich in nature, this oxygen attacks on this sulfur because sulfur here is electropositive in nature. Attacks on the sulfur and this one of the chlorine is knocked out. So this kind of species is getting formed. So this oxygen positive charge is neutralized after this hydrogen is leaving. Okay. So now one of the Cl which is knocked out here will attack on this particular hydrogen and will lead you to the formation of this acid chloride. So when you treat the acid with SOCl2, you will end up with having an acid chloride in hand. Okay, is it clear or not? The particular mechanism.
Once again, repeat, ma'am.
Okay. See, if you have an acid in the system, okay, so here, as we know that this carbon is electron deficient in nature and this oxygen is electron rich in nature. So now here also, this sulfur is electropositive. So this oxygen will interact with this particular sulfur because it is electropositive and one of the Cl knocked out. So if the Cl is knocked out, now this Cl which is knocked out again attacks on this particular carbon because now it is also electrophilic now. So now this Cl will interact with this carbonyl carbon with the removal of this hydrogen to neutralize this positive charge. So the side product which you are having here is SO2. How this Cl which is knocked out in the previous step will attack on this carbon and this bond breaking is taking place. So this SO2 will leave with the H and Cl. Either you can show it in a single step or either you can show it in a second step. Here Cl is getting attached to this particular carbon with the removal of SO2 and this Cl minus again abstract the proton and this positive charge on oxygen will get neutralized. So what you will end up is with acetyl chloride. Okay, so the byproducts are sulfur dioxide and hydrochloric acid. How? Because when you knocked out this particular Cl, it again attack on the carbonyl carbon and the removal of this SO2 group is taking place. So this Cl minus, which is now removing from here, will attack with this hydrogen. Either you can show it here like this Cl minus is attacking here and it is neutralizing the positive charge. You can show it in a single step as well, but here they have shown in this two steps. So the Cl minus will attack on this proton and neutralize the charge of oxygen to give you this particular acetyl chloride. Now it is clear or not?
Clear, ma'am.
Okay. So if you have acid in the system and you treat it with SOCl2, we will end up with a acetyl chloride product. So if we have this kind of system, now what will happen? This OH will get replaced with this Cl. So what will we will end up with a CH3 CH3CO Cl kind of moiety, right? So they have treated it with now benzene in the presence of anhydrous AlCl3. It is nothing but a Friedel-Crafts acylation reaction. If you recall it, it is a Friedel-Crafts acylation reaction. So in the Friedel-Crafts acylation reaction, we have this kind of moiety, right? We are ended up with this kind of moiety, the Cl and with CH3. because we have acetic acid, and this acetic acid OH will get replaced in the case of SoCl2 with Cl. So now we have this kind of moiety, and they have treated it with benzene and in anhydrous aluminum chloride. So this Cl will knocked out, and a carbocation is getting generated at this carbonyl group. So this kind of species is getting generated, which react with benzene ring to form this particular resonating structures to give you acylated product. So this is nothing but a Friedel-Crafts acylation reaction, right? Is it clear? Is it clear or I have to repeat?
No, ma'am. Yes, ma'am.
Okay, so you have learned about this Friedel-Crafts acylation reaction, right? So what happens here? The Cl will knocked out and a carbocation is getting generated. As you know, this benzene ring is electron rich. Now it will attack on this carbocation, and this CO get in the conjugation, and this kind of species is getting formed. Now it will again come down, and this hydrogen will eliminate to give you again the aromaticity, because here in the case of this, aromaticity is getting disturbed, right? So it will regain the aromaticity, and this kind of species is getting formed. So we will end up with a PHCOCH3. So now they have treated this PHCOCH3 with HCN. So hydrogen cyanide, right? So in the case of hydrogen cyanide, now it will not give you a substitution reaction. Instead, it will give you a nucleophilic attack. Why? Because there is nothing to substitute, right? There is no leaving group which is present in the system. So now it will act like a nucleophile. So this HCN will attack on this particular carbonyl carbon as it is electron deficient, and it will go like this. Are you agree with me?
Yeah, ma'am.
Yeah. So it will attack on this particular species, and it will go with the formation of this kind of structure. This this O minus will abstract a proton from the system, and an alcohol is getting formed. This kind of cyanohydrine is getting formed, right? We have talked about this cyanohydrine. So this cyanohydrine system, we have talked, and it is getting formed here. Now the second step is the hydrolysis. They have just do the hydrolysis of this system. So we have learned about this. If in the case of CN, if we do the hydrolysis, what will happen? That this CN moiety will get converted into acid moiety, right? By the mechanism which is we have just now studied. This mechanism will lead you to the CN. In the presence of water, it will hydrolyze to give you acid, right? So same case here. If you hydrolyze this particular moiety, the cyanide will go into the carboxylic acid. So we will end up with this kind of thing. The correct option is, just tell me the correct option, which is the correct structure of D.
Option B, ma'am.
Option B. Yeah, option B will be the correct option, right? So is it clear? I'm
Yes, ma'am.
going to the next. So problem 7. See, what is happening here is you have to justify the rate of the reaction. So rate of the reaction, we have talked about, if this electrophilicity of this carbonyl group is high, then the nucleophilic attack on this carbonyl carbon is very much higher, right? Facile, right? So we have to justify the rate. So what is this Z which is present adjacent to this carbonyl carbon? This is it A, B, C, or D, which is increasing the rate of this nucleophilic attack. So nucleophile we don't have to worry about, because I have told you that in the case if the nucleophile is bulky, then we have to consider the steric hindrance. But they are not justifying which is the nucleophile. They are not asking about the nucleophile. Okay, so steric hindrance doesn't come into play. What system we have to figure it out, that how which is the more electrophilicity nature of this carbonyl carbon when it is attached to this Z group. So now we have to look at the Z group only. So if the Z group is this A, then what happens, that this carbonyl carbon is present in the conjugation. See, it is an anhydride kind of thing, right? So this carbonyl, this oxygen lone pair is in conjugation with this carbonyl, right? So which makes a partial double bond character between this C and O, right? So it will decrease the electrophilicity of this carbonyl carbon. If we consider that Z is the A group. Now, if we consider that Z is B group, again nitrogen is more facile to electron donation than oxygen. So here amide kind of thing is there, and the nitrogen lone pair is present in the conjugation with this carbonyl carbon. So it is although increasing the electron density at this carbonyl carbon. So it is not making it electron deficient, right? Again, in the case of this, we have an oxygen which can uh, which can take part in the delocalization, right? But in the case of D, as we know, if you substitute with an acetyl chloride, if you talk about an acetyl chloride only, this Cl. So if this Z is Cl, then what happens here is Cl is electronegative in nature, as we know. So it will abstract the electron density towards itself. So now it will make this carbonyl more electrophilic in nature. So just tell me which is the fastest rate of the reaction if Z is which is fastest.
If the Z is a Cl, ma'am, then the reaction is fastest, ma'am.
Yeah, if the Z is Cl, then the reaction is fastest because in the case of Cl only, it will increasing the electron deficiency at the carbonyl carbon, and now the nucleophilic attack is much more facile. But all the three A, B, C case, we have seen that some donor atoms are there, so they have taken part in the conjugation, and now they are assuming a double bond, partial double bond character between the particular moieties, and they will decrease the electron deficiency at the carbonyl carbon. Sorry, increase the electron density at the carbonyl carbon. So it will not decrease the electron deficiency. It will, although making it much more electron dense. Okay. So only the option D will make you the electron deficient carbonyl carbon, and the rate of the nucleophilic attack is very high. Okay. So so due to the better leaving group, we can say that this is more facile if we have this ClSZ. So coming to the problem 8, now they have set off the reaction. So first of all, they are taking a methyl bromide and reacting it with magnesium in the presence of ether. So they are asking what is the compound C. So we have to name it. So first of all, they are treating this methyl bromide, this Rx, with magnesium. So here the reaction is the Grignard formation. So what happens here is, and Grignard formation is taking place. So this Rx bond, that is this methyl bromide bond, magnesium get inserted. So this A species will be what? Methyl with the magnesium, sorry, with the magnesium and Br. Okay. So this is what A species is. It will leads the formation of Grignard reaction. So this, when you treat an alkyl halide with magnesium, it will give you formation of organomagnesium halide species, which is a Grignard reagent. Okay. So A will be CH3MgPr. Now they have treated it with an aldehyde. So if you treat the Grignard reagent with an aldehyde, this H, this H. Okay. If you treat it with this aldehyde, what happens? See, here magnesium is positive in nature, this is electrophilic, and this is nucleophilic, as we have talked about. So this is the nucleophilic part which is to be reacted. So this nucleophile react on this carbonyl carbon. It will react on this carbonyl carbon, and this will go like this, like this. Okay. So this R group, which is nucleophilic in nature, this nucleophilic attack will takes place, and a tetrahedral intermediate is forming here. So which abstracts a proton in the acid workup, and an alcohol formation is taking place. So our next step here is also water. So it will abstract a proton from the water, and an alcohol is getting formed. So now if you have this this kind of thing. See, if you have this OH, this methyl, this methyl species, this methyl, okay, and this hydrogens. There are hydrogens. So just name these species. What is this? What is this? CH3, CH2, OH.
Ethyl alcohol.
Ethyl alcohol. Very good. So this is the option. Correct option is D. Ethyl alcohol. We will end up with an ethyl alcohol. Have you gone? Just see this. First of all, the first step is the Grignard formation. After that, this Grignard is reacted with aldehyde to form an alcohol, and after that, this B will take up the proton from the system to end up with an alcohol. Okay. This is how the mechanism will go. Is there any problem?
No, ma'am.
Okay. So the question number 9. This is the set of reaction which is happening. Okay. Now the problem number 9 is in a reaction involving ring substitution of C6H5Y, the major product is meta isomer. So the group Y can be. So they are saying that the benzene ring having one of the Y group, that is Cl, COH, NH2 methyl. So the major product is the meta isomer. Meta isomer, they are having the major. So what is the group Y which can give you a meta isomer in major? So if you substitute Cl with benzene ring, that benzyl, oh sorry, with benzene ring, if you have that Cl group, this Cl. Now this Y is changing. Now we have COH, NH2 and methyl. So they are asking the major product is meta. So what can be the group Y? So first you have to see that for the electron withdrawing groups, if we have the electron withdrawing group which is attached to the benzene ring, that is like COH, we have this kind of resonating structure. So the ortha, which is here, ortha, meta, this meta, and this para. Okay, so it's ortha, meta, para positions of the benzene ring. So if you have the electron withdrawing group which is attached at this position, then the ortha and para, both the electron density at these positions are getting reduced. So the nucleophile which is going to attack now is not, so the electrophile which is attacking, so the electrophile which is coming here, because the benzene ring is electron rich in nature, so now benzene ring will attack to a electrophile. So tell me that does the electrophile come at the ortho position in the case of electron withdrawing nature? No, because here the ortho position although is very electrophilic in nature now because of the electron withdrawing group which is connected. So the ortho or para positions having less electron density at this position. So now the position which is left for the electrophilic attack is the meta position, because now in the case if we compare ortha, meta and para, ortha and para position are less electron rich instead of meta. Now meta having more electron density than ortha and para. So the electrophile will get attached to a position which is more electro dense in nature. So electron dense in nature is here. So it is the nucleophilic space. So now it will attach to the meta position, this electrophile. So, see, okay, is it clear?
Ma'am, once again repeat that, ma'am.
Okay. See what happens when you have a benzene ring, okay, and you have an electron withdrawing group like COH, acid group, or some nitro group, which is there in the system. If you have some electron withdrawing group which is attached at this position, so it will abstract the protons or it will abstract the electron density towards itself, right? It will withdraw electron density, right? So it makes this ortho and para position very very electrophilic in nature due to these resonance structures. Now this ortho position and the para position is electron deficient in nature. So if one electrophile has to attach to this particular benzene ring, because benzene ring is like, although electron rich, we know that these pi bonds are electron rich. So now if one of the electrophile are need to be attached to this particular benzene ring, so which is the position which it prefers? Does it ortho or para or meta? It will prefer the meta position. Why? Because ortho and para now is electron deficient in nature. Just try to understand that the electron withdrawing group will abstract the protons, will abstract the electron density towards itself, and that is why what happens, that this adjacent oxygen ortho position is getting low in electron density, and due to the resonance structure, this para position is also getting electron deficient. So the position which is not getting that much electron deficient is the meta position only. So this electrophile will prefer the attack towards this meta position rather than the ortho and para. Now, is it clear?
No.
Yeah. So if this benzene ring has to attack to an electrophile, it will subject it towards the meta position rather than ortho or para, because electrophile is although electrophilic. Now you are attaching it to a position which is although electrophilic, ortho or para. So now it will not stabilize the system. So that is why the electrophile is now getting attached to the meta position instead of ortho and para in the case of electron withdrawing groups. But if you have electron donor groups, now electron donating groups like Cl, methyl, it will increase the electron density at the ortho position, because it will now give give their electrons towards the benzene ring. So it will increase the ortho and para electron density. So if our electrophile has to attach, in the case of this particular electron donor system, if an electrophile has to attach, so just tell me which is the position it will prefer. Does it ortho or para or meta?
Ortho and para, ma'am.
Yeah. So it will prefer an ortho and para position, because now these position are electron density is very high at these particular ortho and para position rather than the meta position. So is it clear?
Yes, ma'am.
Yeah. So if it is clear, is coming back to the question, they are asking that if you have an substitution, that is Cl, COH, NH2, and methyl, which of them is going to give you a major product as meta isomer? So which is going to give you a meta isomer as a major product? If Cl is there at the benzene ring, this Cl will doesn't affect the ortho and para attack that much, so the electrophile can attach to ortho and para positions, right? So it will not lead to formation of a major product like meta isomer. In the case of also and D also, these are the electron donating groups, NH2 and methyl. So if they are electron donating, they are increasing the electron density at ortho and para position more. So electrophile will prefer the ortho and para position. So meta isomer is not going to give you the major product, right? But in the case of acid, electron withdrawing group, so this meta position is the major, because these ortho and para are electron deficient in nature now. So now tell me which of these will give you the meta isomer in the major product A, B, C, D. Which?
See, ma'am.
Option B, right?
Yes.
So this B will lead to give you a major product as meta isomer, because it is electron withdrawing in nature. Okay. So is it clear?
Ma'am.
Okay, so I'm going to the last question of today's lecture. See, here in the problem number 10, they are asking this again the same thing. In the above reaction, the product P, we have to figure it out. So, which is the product P? We have to figure it out the structure. So, here it is also a Grignard reagent PHMgBr. Okay, so they have treated it with the carbon dioxide. So what happens here is the mechanism goes through like, first of all we have the pH in the case, in the place of R, we have pH. So pH, that phenyl group will interact with this carbon dioxide molecule. Here the carbon dioxide molecule, the carbon is electrophilic in nature. So this nucleophilic attack will take place at this carbonyl carbon, and one of the oxygen got a negative charge. like this. Okay, so our tetrahedral intermediate is getting formed again. So now they have treated this particular compound 1 with acidic condition. Now with water they have treated it. So now what happens? This oxygen will again abstract a proton from the proton source and will end up with an acid, with an OH group. So in turn you will end up with an acid. Is it clear the mechanism? Because we have the nucleophile here in the system, that is the Grignard reagent. We have this kind of nucleophile pH minus. So this nucleophile will first attack to the carbon dioxide. Carbon is electron deficient here. So one of the oxygen will get a negative charge, and the counterbalance is the counter anion is here is the counter ion is the magnesium halide. So now, when you treated it with a acidic condition, this oxygen anion will abstract a proton from water and will end up with an OH group. So now, what you got is the acid group. So P will be an acid. So which acid? Just tell me the correct option.
Option A, ma'am.
Option A will be the
Carboxylic acid, ma'am.
yeah. So option A will be the correct answer. So this is the benzoic acid. Okay, is it clear?
Yes, ma'am.
Okay, very good. So from now we just close the lecture, today's lecture. So I hope these problems are clear to all of you. If you have any problem regarding the solution, just tell me in the next lecture and I will let you know the answer again. Okay, and I'm just uploading this lecture on the YouTube. Just have a look on that, and if you have any doubt, just ask me. Okay, thank you so much for patiently listening me. Thank you for the interaction. Okay, so I'm just closing the lecture.
Thank you.
Okay.